Okay, Laplace domain and Kirchhoff's laws, then element-IU relationships for resistor, coil, and capacitor. Well, what regards Kirchhoff's laws, they can be transferred easily from time domain to Laplace domain using the linear property of linearity. So we may say that for Laplace currents, the current Kirchhoff's law is satisfied. Also for Laplace voltages, voltage Kirchhoff's law is satisfied. Now, IU relationships transferred from time domain to Laplace domain for these three basic elements: resistance, inductance, and capacitance. So let's start with resistance. Following this, at the left we have this time domain relationships with a constant of proportionality R between current and voltage. Following, using a property of linearity, we may find these equations in Laplace domain. Multiplication by a constant corresponds to multiplication by same constant in Laplace domain. And this is same resistor expressed in Laplace domain. Now a few words regarding power and energy. Resistor is energy dissipating element. Energy is dissipated as a heat, doesn't matter whether it is DC current or time varying current. The instantaneous, in case of we have time varying current, our power is instantaneous power. It is some function, and energy, it is the integral of this function, and these formulas are giving the energy which is dissipated as a heat on a resistor. Now, exemplary waveform. Let's say we have an exemplar piecewise linear approximation of a waveform of this form. This is voltage. Let us assume that our constant of proportionality is 1, and we have exactly the same drawing for current, with only difference that now we have amps instead of volts. What regards instantaneous power, we have to simply find the square of current and multiply the square of current by R to obtain the instantaneous power, which is nonlinear function. And what is important here is energy. Energy, as you know, is an area below the curve, and it is integral. It is area below these curves, which is depicted on the next slide. As you see, this area, shaded area, is always positive. This means that energy is, the power is always positive or zero, never negative. And this corresponds to energy which is always positive, doesn't matter in which instant of time energy is positive, which means it is absorbed energy and dissipated as a heat. Now, capacitor energy, two energy storage elements, capacitor and coil. First, capacitor, it is an element that stores energy. The basic relationship is well known to you. The charge is proportional to voltage and constant of proportionality C, a capacitance in farad. And now from this equation we may find equation that relates current and voltage, and C is constant of proportionality between charge and voltage, not between current and voltage. So this is the formula. We may convert this formula to integral formula, and then we may transfer these formulas into Laplace domain using a property of linearity and differentiation or integration. At the right side you have these two formulas. As you see, the first formula, current, is algebraic sum of currents, which means that we may model this formula by parallel connection. Here we have voltage being a sum of voltages, which means that we may model this equation by a series connection. In Laplace domain, then, we have equivalent diagrams of practical capacitor with initial condition, practical capacitor with initial condition. This is capacitor without initial condition. Initial condition, capacitor initial condition, is voltage across the capacitor. And this is parallel equivalent circuit. This is series equivalent circuit. Capacitor without initial condition, and here initial condition is taken into account as a step. This corresponds to a step in time domain. This corresponds to impulse in Laplace domain. In time domain. In Laplace domain it is C U sub O. Now a few words regarding energy, which is stored in a capacitor. This energy can be calculated from the same formula. Energy is integral from the instantaneous power. If we set this into this equation, we obtain the following relationship, the following formula that expresses energy, which is stored in a capacitor. Please observe, actually I think that this formula should be learned by heart, and energy, which is stored within a capacitor, is obviously proportional to C, the circuit constant, but also it is proportional to the square of instantaneous value of voltage. Instantaneous, so at the instant of t, the energy is designated only by instantaneous value of this voltage. Doesn't matter how this voltage reached this value, doesn't matter what was the history of this circuit. The energy at the given instant of time is designated only by instantaneous value of voltage. Okay, same waveform. Now after differentiation, we will assume for simplicity that C is 1 farad. Then after differentiation of this voltage waveform, we obtain a current waveform, and below we obtain, as a product of these two, we obtain the instantaneous power. This shaded area is energy. As you see now, the instantaneous power can be positive, can be negative, and energy then can be positive, absorbed, or released. This is energy storage element. In capacitor, energy is only stored, and then this energy can be given back, can be released. For this exemplary waveform that we have at the left, at different instances of time, for t0 we have assumed that we have zero initial condition, voltage is zero. Then a capacitor is charged during these first 2 seconds up to the 2 watt second. This is energy at this time instant. It is 2 square multiplied by 1 divided by 2. There is no flow of energy during between 2 and 4. We have the same instantaneous value of voltage. That at t equals 4 we have the same 2 watt second. Then we have discharge phase from 4 to 5. It is discharging of capacitor. At this moment, 5 seconds, no energy is stored, and then capacitor is charged again. Capacitor is charged again, we have reversed, voltage and current are now negative. The capacitor is charged again, energy is stored. At the time instant of 6, we have once again 2 watt second, then we have discharge up till 7 seconds, and then no energy inside the capacitor. A very similar reasoning can be repeated for coil. Coil, it is an element that stores also energy. Coil is described by its inductance. Inductance is constant of proportionality between a total flux produced in magnetic circuit and current that produces this, that flows through the winding. And this inductance, self-inductance, as also we have a mutual inductance, but now we will discuss only self-inductance, and I will use term inductance, which means self-inductance, is proportional, is designated by number of turns, square of number of turns, designated by the material, mi sub r, permeability of this core, and SL, they describe dimension of the core. The unit is Henry or millihenry or microhenry. Then transformation from time domain to Laplace domain. This is equation relating voltage and current after differentiation of this. And then using property of linearity and property of differentiation, we obtain these equations. So we have obtained actually very similar equivalent diagrams. Now we have in a series equivalent diagram, we have a voltage source which has in time domain a character of Dirac's function, and in parallel circuit we have a current source which has a character of step function in time domain. Energy, following very similar reasoning as before, energy is designated. Energy which is designated which is stored in a coil is designated by instantaneous value of current, a square of this value. multiplied by L and divided by 2. And here on this slide, you have actually repeated the slide that you've seen already. We have only just swapped current and voltage, and nothing else. Okay, so obviously we can also discuss capacitor and inductor in hydraulic circuit. We have hydraulic analogy. I'm not going to discuss this issue now on. You may study this slide, or you may Google to find capacitor inductor in hydraulic system. And now the last slide, summary. On this graph you have these relationships between in time domain between 4 circuit variables. We have 4 circuit variables: voltage, current, flux, total flux, and charge, and they are related, each pair except Q and phi t, they are related by these equations that you have on this slide. Okay, so that way we have discussed, it is a memristor which is missing element relating charge and total flux, but I'm not going to discuss memristor. That way we have completed this part of transient analysis. Thank you for your attention.